So let's start. Today we are more or less concluding the part of the lecture regarding the basic definitions, how to measure sparsity or denseness of graphs. And we're having the previous lecture, the previous two lectures, was a lot of definitions and small lemata and small observations. Today we have got two larger proofs. So today we are proving some stuff, which is actually not that trivial. It's not a 5-minute proof. So let's start. The first thing we're going to look at is to look at something which I will call congested minors. So let's make definition. So remember that we have had the definition of shallow minor. Right? We have this definition, and there was a shallow minor, H, let's say shallow, I will write this, a shallow minor of H in G is what it was. I mean, the minor model, we had the branch sets for every vertex of H, and yeah, so there was a collection of, say, UH for H in V of H. Each UH is a subset of V of G and it's connected. And then edge in H projects to an edge between these two guys. Yeah, so an edge. So for every H1, H2 in we say that UH1, I would say that UH1 and UH2 touch, which means that they have an edge between them. Yeah, so there's like some edge that exists. H1 prime in UH1 and H2 in UH2, such that there's an edge. This AH H2 is an edge of G. Yeah, so they touch, so it means that there's an edge between them. Okay, that was a minor model. And we had here, this is connected of radius at most A. That means shallow. And that was minor model, this is shallow minor model. And now I want to add congestion to this definition. That means I want to, and there were this joint, yeah? So there was here this joint, UH pairwise this joint. Okay, pairwise this joint. Okay, and now I want to add congestion, so I want to replace pairwise this joint with the ability to use every vertex a constant number of times. So I will add here congestion C. Where C is another integer, here. I will cross this on out and say that for every vertex V in V of G, the number of this H, so that V is in UH, is at most C. Yeah, the number of so the number of vertices of H, I mean, this sets, every vertex of G can be used in most C sets of this minor model. And now touch means that if there overlap, there also touch. Okay? Or that means that UH1 intersection UH2 is an empty, or this one. Yeah, so the definition is that I consider that an edge is happy if these two sets overlap. And I also say, I say that sets can overlap, but every vertex can be used in most C of these sets. So the previous minor models correspond to congestion 1. Then every vertex can be used at most 1. Then this part is not possible, and every edge needs to be realized as a real edge. This definition really corresponds to a normal model if you take a graph and blow up every vertex into size C clique. Yeah, so I would say that this is more or less the same as like replacing taking G and replacing it's like I would call G dot KC, which means that every vertex replaced with size C clique. Yeah, that means that every vertex is in a size C clique, and you can use different copies of a vertex for different branch sets, and this corresponds to like using every vertex a multi times, because you can use different vertices of this clique to branch sets, and the fact that you blow up with a clique corresponds to the fact that if you overlap, then there's an edge between this clique, and this corresponds to satisfying touching. That there's like realizing an edge of the model. Okay, so this is congestion, and as we will see on tutorial, if you forget shallowness and you think of congestion 2 or congestion 3 models, minor models, and you forget about this diameter thing, then like this pies of models of congestion 1 models and congestion 2 models of a graph can vary greatly. I mean, we see that there are graphs when congestion 1 models are very restricted, and congestion 2 models can be essentially everything. On the other hand, what I will just prove in the next half an hour is that if you look at constant radius minor models, I mean bounded shallowness minor models, adding congestion doesn't change much. And this is sort of an argument why these notions of bounded expansion and lower dense classes are useful or robust, in the sense that they're robust if you change the model from, minor models from being disjoint to minor models, you can use every vertex at most 10 times, then the constants change, but the class, we had a lemma saying that the constant bounded shallow minor models of some graph class is still bounded expansion, is still a bounded expansion, and here we prove that bounded congestion, bounded shallow and shallowness minor models of some bounded expansion graph class is again bounded expansion, that you can control these grads, the density of the models, of the minor models inside such models similarly, that is a constant blow up. So this is like, in some sense, our theory which we are building is resilient under changing congestion from 1 to 2 to 3 up there. And that's surprisingly useful in many options. Okay? So the theorem, what I want to say is that let's look at the following thing. I have got a number of complicated formulas here, that's why I'm using this. So let's say that let's do the following. Let's, if G hat, so the lemma which we are going to prove. So we have got some integers ABC, integers, and there's a graph G, and G hat is congestion C, a shallow minor of G. So I have got a minor of this one, and now I want to say that the grads of these ones are bounded by the grads of these ones. Yeah, so I want to say that delta B, this is the unused integer of G hat, will be bounded by C minus 1 over plus 2C minus 1 times 2AB plus A plus B plus 1 times the grad, and here we 2AB plus A plus B of G. Okay, this is the formula. On qualitative level, what it says that if graph G has got small density of shallow minors, and from class of bounded expansion, lower dense, has got small density of shallow minors, then G hat also has a small density of shallow minors. It's not that small. I mean, since if you take this numbers for larger radius, multiply by a large constant, and then add something on top of it, but this is still bounded. So in some sense, if all these guys are bounded, then all these guys are bounded. If this guy comes from class of bounded expansion, then this operation of taking congestion C a shallow minor produces class of bounded expansion. Okay? So this is what we have here. And yeah, let me now give the intuition of this formula. This term is the density of this clique that we are putting inside every vertex. Yeah, this is the density of a clique. This is like, this corresponds to these new edges that we can have by overlapping branch sets. Okay? And this should not be a surprise, because this is like the radius that we needed to look at when we looked at the A shallow minor of a B shallow minor, B shallow minor of an A shallow minor. Yeah, we are having here A shallow minor, and then we are looking at B shallow minor of this A shallow minor. So it shouldn't be a surprise that we are looking at this radius up there. And this term up here will correspond to, like, okay, we have got this B shallow minor of an A shallow minor. This is what this term speaks about. Yeah, and now there's a lot of overlap of the branch sets because we are doing congestion on the way there, and this will come up from calculations like what's the real congestion of our model and how does this graphs relate to each other. So let's try to prove this lemma. Okay, so this formula is quite huge, but I hope we'll be able to do it. So let's try. Let's go with the proof. So we want to bound the density of such things. So the natural thing is to take a B shallow minor of G hat. Yeah. So first let's take a bigger chalk, and So we have got, yeah, so first let's look at the minor model of this guy here, and then we look at the minor model of G hat, B shallow minor of G hat. Okay? So first let's look at the minor model of G hat in G. Well, these are sets, let's copy this notion. So these are sets U V for V in G of G hat. Okay, these are the sets. Okay, and there are congestion C A shallow minor model, and then we have got another minor model of some graph H in G hat. G hat. Okay, so this is the minor model of G hat, and let's call them W V W H for H in V of H. Okay, so these are the two minor models having structures. So as before, we said that as before in the proof that A shallow minor of a B shallow minor is 2AB A plus B shallow minor. Let's take the union. So let's define. So I will write it here and then move up there. So let's define for H in H. I will call it now EH. It's the natural thing here. We have got this minor model. So this is like some blob up there. This VA, WH. This is a blob, but inside every element of this one is element of G hat, which actually corresponds to some branch set, some blob in G. So we take the union of all these blobs. Yeah. So this is the union over W in WH U. Okay, so I mean the picture is like the branch set here actually is a collection of branch sets in this minor model. So we take the union of everything, and as before, this was exactly the same argument that was in the previous lecture, that A shallow minor of a B shallow minor is 2AB plus B, was that the radius of IHH in G is bounded then to AB plus A plus B. Okay, because I mean inside every branch set of G hat in G, you can go in this sense 2A, and this means that there's like B steps up here to go anywhere. Okay, this was like as before. And let's take a center. I mean, I want to say pick a center. So let's call it CH. Inside IH is the center. Okay, this is the center. Okay, this is like the center vertex that has got everybody else within this radius. Okay, and yeah, so this is this. And now what I want to do. I want to bound the density of H. So what I really want, I want to count the number of edges there. Okay, I want to count the number of edges there, and then we'll be like, yeah, there will be a bound. So I want to count the number of edges. Let's go to this board and let's do the count. I'm wiping out the definition, unfortunately, but I think everybody already started. So the intuition is as follows. So H has got an H can have some edges, and there are edges which come from the fact that these things really overlap a lot, and we'll call them degenerate edges. So let's partition into EH into E1 million 2, and E1 are these edges H1, H2 in E of H, such that the centers are the same, and the E2 is the rest. Yeah, so I first count the edges when the centers are exactly the same. Okay, because what I want to do because this is a normal minor model, but this is a congestion C minor model up there. Every vertex can be in at most C sets IH. Okay, at most C sets, because we take the union of disjoint sets. I mean, this VWH are disjoint, but every vertex can be at most C sets U of V. That means that one vertex can be in at most C sets IH. Okay, we have got again still like it's like a congestion C minor model in a G of G H in G. Okay, so now what we want to say, we want to somehow flatten this model to get a model of not congested model, and say that, okay, after flattening, this model needs to have a few edges, because nabla of G controls the number of edges there, but during the flattening, we survive a constant fraction of all the edges. Okay? So now what we are doing, we're counting number of edges for H and trying to relate it to somehow like a flattened model. So now not congested model there. We want to take from H, forget about a lot of parts, but get a non-congested model up there. So first we count the edges that we have got no chances of surviving. That means the edges that are actually connecting, in a sense, like the centers are the same. They're like two mostly overlapping branch sets, or that's how we imagine there. So, but that's quite easy. I mean, D1, what's bounded? I mean, D1. I mean, in one place you cannot congest more than C centers. Yeah, you cannot congest more than C centers. So this is really sum over H in what I want to say. I want to sum over the size of the premier. So I want to say V in V of G, this number of okay. So I want to think of C as a function. So this is C to minus 1 of V. So that's the number of H. So that's CH equals V. Choose 2. Okay. So how many edges of this type there are? Well, the number of pairs that collide with the same center. That means that for every vertex in G, we look at how many edges really. We look at how many edges have this as a center, and every pair of these guys is 2. And I want to bound it brutally by just the number of vertices of H times minus 2. Okay, because the worst case is that, I mean, this is like easy inequality, saying that the worst case is really when they all cluster in clusters of size C in different vertices. Then there are the most pairs of this type, and then the group in the pairs where there's there's V of H over C, sets of size C choose 2, and this is bound. Okay, you can also like say that this is really like this times this minus 1 slash 2 and bound 1. This is so this is like quite easy, and this corresponds to this term here. This will be this term here. Yeah. Okay. Okay. So now let's go to E2, which is slightly more complicated. So let's go to E2. How to bound E2? For E2, I want to try to select some edges of H and choose only some of them to make a still quite dense topological minor. Okay? So I want to make what we want to do, we want to choose some subgraph H hat inside H by choosing V of H hat being V of H and E of H hat being some subset of H2, and I want to choose a subset such that there will be like a topological, this will be topological 2AB plus A plus B, shallow minor model, shallow topological minor of G. Yeah, so I want to use the centers as anchors to get as dense as possible, from this H extract a shallow topological minor of a G without any congestion. Let us do it. So we have got, so for every, so these edges connect two guys from different, with different centers. So for every H1, H2 in E, we get the path H1, H2 from CH1 to CH2 that go through IH1 and IH2. Okay, so these are this union of these branches. We said that they're like of radius 2AB plus A plus B. Okay, that's what we proved there. And they touch each other. There was the definition of touch somewhere here. And that means that you can connect these two centers by a path. And this path has got length at most 2AB twice this radius. Yes, and this is the length. pH1. Okay, so there's a path between them. I mean, you go through one barn set, go through the touching place, and go to the other place, and this is the path. Okay, good, great. But but these paths can intersect with each other. Okay, every vertex can be in the most C sets IH, which means that these paths can intersect with each other quite a lot. Okay, but they cannot intersect too much, in the sense that because every vertex can be in at most C sets IH. Okay, what I want to say is that there's like these paths can't overlap too much. And I want to say that, the maximum degree. Let's do now the auxiliary graph. Let's now make an auxiliary graph when L vertices. I run out of letters, so let's call it J. So vertices of J are these paths pH. Actually E2, and then H means that they intersect. H they're intersecting internal vectors. Intersect. I mean, intersecting in a trivial way. I mean, if they have the same starting point, then that's fine. Okay, and okay, actually won't be topological minor. Let's go this way. What I want to say is that now I want to say if they intersect, but they should be like, they should intersect. Okay, so what does it mean to intersect here? That means that they intersect in like surprising way. Yeah? So if I consider path from CH1 to CH2 and the path from CH1 to CH3, then I'm fine if these paths start together in IH1 and then separate and then diverge to each other. That's not a bad intersection. The bad intersection is that if there's intersection inside different set IH. I mean, so if these guys have got a common endpoint, these edges, then these paths within corresponding IH can intersect, but they cannot intersect when. But I don't want. I want the conflict to be when they intersect on the wrong set up there. Okay, if there's like, if they're intersecting on the, I mean, in the sense this path has got a part colored H1 and the part colored H2, and the wrong intersection is the intersection of the part colored with wrong vertex. And now my conclusion is that this graph is actually of bounded degree. That this graph, the maximum degree. Okay. Well, the point is that a vertex can collide on at most his length. At most, his length times c minus 1, twice his length, this is his length, times c minus 1. If this is his length, and this is the congestion, how many guys he can collide with. Yeah? Every path on every vertex, because colliding means that there's a different branch set at this moment. There's a different path, so at every vertex, the path can collide with at most c minus 1 other paths, which means that this colliding graph, this auxiliary colliding graph, has got bounded degree, which means that it has got an independent set of size like this over this plus 1. Yeah, I mean size of just this independent set over this plus 1, and we have what we want here. Let me wipe out the lemma statement for that one. Let's keep the formula. That means that there is an independent set in J of size number of vertices, of size of 2 over this thing, 2 times c minus 1 times AB plus A plus B plus 1, because this is degree plus 1, maximum degree plus 1, and this corresponds to a congestion, this corresponds to this minus. So size of E2 is smaller than this thing times this big thing times nabla 2AB plus A plus B of G times number of vertices of G. Okay, yeah, because I mean, I obtained a normal, this radius minor model, shallow minor, this shape shallow minor of G, which means that its number of edges is bounded by this one, because that's the definition of this nabla. Okay, and I lost this fraction of edges on the way there. I mean, I reduced it there, so I hope it's okay. I was trying to make some intuition. There's a proper proof in the notes if you prefer, but the intuition is that, hey, if you look at this path, actually like the colliding graph, I mean, which two edges you cannot keep at the same time to keep a non-congested model, is actually kind of bounded degree, because in every place you have got only like collision with C-1 different edges. Good. So this is something. So now let us discuss the intuition standing behind it. The intuition is that there's some technical things when you do the proof, but the message is that the notion of bounded expansion is resilient towards like blowing a vertex into constant size clique, or using a vertex constant number of times in the minor model the other way. So, and this is surprisingly useful in many operations. So later we learn about generalized coloring numbers and orderings, when the fact, with these notions, the fact that blowing a vertex into a clique doesn't, I mean, only works as constants, but keeps you within the class of bounded expansion, will be much more obvious. But here we have got some pretty decent formula of how that the grads or the nablas of one relate to nablas of other graph class, and yeah, that's why we show this proof. Good. So that's the first thing, and I hope, I mean, I conveyed the idea what's happening there. The other thing what I want to do today, and I will be slowly wiping out the board to do it, is I want to prove that, so far we had for nowhere dense, now we move for nowhere dense graph classes, so I want to use this remaining space here that's the least useful, as the least useful to recall what was the nowhere dense graph class. Yeah, the graph class G was nowhere dense. So if and only if there was a graph function f, such that for every radius r, there was no k f of r as r shallow minor of every g. Of every g. And that was the definition, and that was very like, it was like very qualitative in the sense that it says, hey, there's actually no big clique. But for bounded expansion, we said, hey, actually shallow minors have got bounded density. Okay? And now what we want to prove, that the classes of nowhere dense graphs still have got not bounded degeneracy, but small degeneracy. Okay? The intuition would be like, this one is enough to prove that the graphs have got few edges. They cannot be quadratically many edges. There are few edges. And the theorem which we'll be proving here in the remaining of the lecture, theorem what we're proving here is that let me phrase it this once. There exists a function f, I mean for every nowhere dense graph class. If G is nowhere dense, then there exists a function m, which leads from 0 plus infinity to integers. Okay, such that for every epsilon greater than 0 and for every g in this graph class, if this g is sufficiently large, this is like a lower bound on the size of g and of epsilon. So if g is sufficiently large, then it has got few edges. So the intuition is as follows. The number of edges, the average degree of a nowhere dense graph is subpolynomial. Yeah? It's not constant. The average degree here is like n to epsilon for as small epsilon as you want. So, I mean, you can think of like, okay, it allows n polylog n. It allows things like n times 2 to the root log n, or these types of expressions, but doesn't allow n to 1.01. This density is, I mean, this number of edges is too much for the nowhere dense graph classes. Okay? So the theorem says that if graph is nowhere dense, then there's bounded number of edges. And now, because we have proven that, okay, this is the theorem that I want to prove, but look that we have proven that, I mean, this is quite obvious actually, but because again, A shallow minors of B shallow minors or something shallow minors, is that, hey, nowhere dense graphs have got bounded, like small density, I mean, n to less than n to epsilon, but also A shallow minors of nowhere dense graphs is a nowhere. If you take a nowhere dense graph class and take all A shallow minors, this will be again a nowhere dense graph class with force function phi f, but still, that means that this new function will still have got bounded density. So like all shallow minors of nowhere dense graph classes have got small density. Yeah, I want to color it or actually, like if G is nowhere dense, then there is a function m. I would write it this way. There's a function f which takes an integer and 0 plus epsilon and it gives an integer and says that for every g epsilon greater than 0, for every integer a and for every graph g in this graph class, the number of edges, like the, and if h is an a shallow minor of g, then the number of edges of h is at most f of a epsilon times the number of vertices of h to 1 plus epsilon. So like the shallow minors, the A shallow minors have also got this type of density, 1 plus epsilon in the exponent, with some huge constants in front, depending on the epsilon and the shallow minors and the graph class we are doing. Okay, so we proved this one today, and we'll be proving, we're giving a proof which is not optimal. I mean, the question is like, you see that if you're really into like some asymptotics, then how bad this function m is, or do you really can have this statement? Can you just say something like, hey, it's at most n to twice 2 to the root log n, or something like that? I don't really know what's the correct answer. I think there's a number of open questions here. But I want to give one understandable proof of this one, which is not, which doesn't give the optimal relation of how huge m can be or what's actually the relation to these parameters here. But I think it's understandable. It's actually quite interesting. I mean, it's quite a different proof, different type of proof that we already used. But it's quite useful. So this is the statement. I'm drawing a line here. I'm wiping out the rest and doing the proof. Okay, so let us try. The idea is as follows. So it will be like quite, okay, so the structure of the proof is quite non-standard. So consider yourself warned, let's try to do it. We want to have a graph, a nowhere dense graph class, that's too dense. I mean, it's large, but too dense. And we want to make a small contractions, actually one shallow minor of this graph, to make it even denser. Okay, so we want to have the following operation. We start with some graph. Okay, we start with some graph G, call it G0, which has got a lot of vertices. So it has got n vertices. Okay, and more than n plus 1 epsilon, and this n is larger than some n of epsilon. Okay, this is more edges, and we want to make some contraction, some one shallow minor. Okay, and get some G1, which will be still quite large. So what we'll get here, something like some number of vertices will be like at least n to 1/2 minus epsilon half, I believe. This will be this number of edges, this number of vertices. So we'll more or less square root the number of vertices, but so this will be like n1, this number of vertices, but the number of edges relative to n1 will be denser. So there will be at least n1 to 1 plus epsilon square edges. Okay? Yep. And this will be one shallow minor, but there will be like a branch set, there will be like or k, something like omega of log n, kt as one shallow minor, for some t being omega of log n. So we have got a procedure that takes a graph with a lot of edges, and assuming that it's sufficiently large, it will find a huge clique shallow minor. This is like huge, log n. This is huge. This is not a constant. This is like huge. This means that this is not a guy from lower dense graph class, right? We have got a log n sized clique inside, or we make one shallow minor and then the graph, which we just halved the logarithm of number of vertices, so this is much smaller, but still quite large, and we get it denser. Okay. So now what do we do? Somebody gave us some epsilon. Okay, and I want to repeat this process 1 over epsilon squared times. So now repeat this process approximately 1 over epsilon squared times. Okay, this is a constant. So epsilon was a constant. This is some huge constant. Okay. At every step, I take one shallow minor of all those previously. So there will be one shallow minor the first step, two shallow minor the second step, four shallow minor. Actually, if I contract the edges, I can duplicate the distances. So we like 4 shallow minor, 8 shallow minor on the next step, 16 shallow minor the next step. Yeah. So in the if iteration, so this is like I started with gi and make gi plus 1. Okay, and so I start with g0. G0 is g, and 1 over epsilon squared times do gi plus 1 is like, so I will write like 4 I equals 0 to 1 over epsilon squared do gi plus 1 is just like this operation of gi. Okay, this operation. And now what happens here? So first, yeah, how many vertices have we? Like the number of vertices of n I is roughly n to 1 over 2 to the I. Okay, I'm ignoring this minus epsilon half. This like, okay, 1 minus, so I'm like more or less square rooting the number of vertices at every step, okay? But I'm blowing up the number of edges, yeah? I'm like adding epsilon squared at every step, and so this will be the next epsilon, it will be larger, so now epsilon squared will be even larger. So what I'm saying here is that the density, so the number of edges of gi, is larger than ni to 1 plus epsilon plus I epsilon squared. Okay? I mean, I'm now doing estimation, so I'm adding epsilon squared. In the next iteration, this will be my new epsilon, so now epsilon squared will be even larger, but ignore this gain. Let's say that we add epsilon squared, the original epsilon squared every step. Okay? So the number of edges will grow, and after this number of steps, it will exceed quadratic bound, and that's contradiction. Okay? So within this number of steps, at some moment we need to get the other outcome. We need to write an exception. Let's call it an exception. This procedure will raise an exception. Actually, there's one shallow minor, okay, which is a large clique. But what's now the problem? The point is that now what we have is that gi is a 2 to the I shallow minor of g. So we have got a constant shallow minor with this size of the vertices, and it has got this clique, yeah, which means that there is a clique. So there is a clique. So exception gives. So now log n is the same. Gives a clique kt as 2 to the I, so 2 to the 1 over epsilon squared shallow minor, with t is larger than, and here we have got some constants, yes? So we have got this, so we have got 2 to the 1 over epsilon squared, so I'm taking this logarithm, so this is like for t1, 1 over 2 to the 1 over epsilon square times this omega of log n coming from here. Okay? So this is still size of log n. So we have got a constant shallow minor of size omega of log n, which shouldn't happen in the, I mean, this was arbitrary graph from our graph, arbitrary dense graph from graph class, which means that we shouldn't get a huge shallow minor. I mean, this is like too large shallow. I mean, for this density, yeah, let's say it this way. So this is my shallow minors. Okay, this is my shallow minors, and because we are from bounded expansion graph, nowhere dense graph class, this should be actually smaller than the function. There was this function that should be smaller than the function of shallowness, yeah, 2 to the 1 over epsilon square, which gives a bound on the n. Yeah, that means that this is some constant, there is some constant here, and this is log n, which means that actually we started from a small graph, and this is our lower bound for n in the procedure. Yeah, so this procedure starts with a dense graph, more than n to the 1 plus epsilon graphs, makes a number of iterations, and cannot make 1 over epsilon square iterations, because then the number of edges is more than quadratic in the number of vertices, which is contradiction. So at some moment it makes an exception, giving a large clique as a shallow minor, which means that, but this large is of size constant times log n, but cannot, this is a constant shallow minor, which means that it cannot be too large because we are from nowhere dense graph class, which means that actually the starting graph must have been smaller. You must be smaller than 2 to the, more or less 2 to the f of 2 to the 1 over epsilon. Okay? So this is the structure. So what we want to say is that so the structure says that if that guy from nowhere dense graph class has got a lot of edges, we can find a one shallow minor which is even denser, and that means that we need to shrink this one to constant size graph within constant number of steps, which means that we started with a constant size graph to start with. So large graph cannot have that many edges. Okay? That was complicated structure. So now let's try to look at the procedure itself. Now let's look at the procedure itself and let's check. Let's see how this one will go. Yeah. So we want to go here. We want to check how the graph goes to a small shallow minor. And the idea up there is to more or less do a randomized construction. So the idea that nowhere dense graph class with a lot of edges, I want to make more or less this one shallow minor at random and argue that either there's a dense shallow minor, or there's a clique shallow minor, or this randomized procedure increased my density. Okay? So let's try to do. So the procedure is as follows. So let's make the operation of GI. Okay? So what I want to do, the new vertex set will be just a random set of guys. Yeah? So I fix a probability P, and my probability will be 2 log n over n to epsilon. So I'm saying this operation I would use GI, so I would call, I will skip the iteration and I'll call it G. So if G is an input to graph, let's look at you can think of the first iteration. I'm just taking this probability and I'm making every vertex, so this, I fix this probability, and I'm making a set A, which will be like the vertex set of the next graph in the series. Just every vertex with probability P goes into set, and with probability 1 minus P goes out of set. Yeah, so A is a random set, so A is got for every P in B of G, V in A with probability B. Probability in A with probability independent. Yeah, so thing goes follows. Every vertex has got its own very biased coin, and with probability P goes into the set, gets marked, or like gets into set A. This is like the important guys we'll have later. Okay? So this will be the new vertex set, and now we want to contract the rest onto this set. Okay? Now what we want to say, we want to take the remaining guys from the class and contract onto set A. So like what we want to construct what you want every W in like v of g minus a contracts onto neighbor and neighbor in A. And this will be like phi g output. Okay? That will be the output. That will be the output. But first we need to non-trivially choose the neighbor we are contracting onto. Okay, we want to contract onto neighbor. Okay, good. Let's try to do it. So the first observation is like how large the set A will be. Well, what's the expectation of the size of A? Okay, so the first thing we want to understand is that what's the size of A? Yeah, this expected size of A. Well, that's easy. Yeah, these are like independent coin flips. This is p times n. Yeah, which is 2 log n times n to 1 minus x. Okay, this is simple. How much it will deviate from this part? Not much. Yeah, we have this that if a lot of guys do independent coin flips, they will be very, very close to the expectation. Okay, what probabilistic statement says it formally? Like we can use Chernoff bound. Yeah, so we will use Chernoff. Is Chernoff, and the form of Chernoff I have here. I have prepared here a form of Chernoff that works, and I have got all the constants put through. Okay. The force is that if I have got x1 up to xn independent identical Bernoullis, yeah, so the probability that xi equal 1 is some. Let's call it Q just to differ from here. Okay, so that's once. And then the expectation, the expectation of the sum xi is of course Qn, but the probability that will differ a lot. So the probability that the sum will differ from the expectation by more than a delta times the expectation. Yeah, so this is like how, if I differ by more than delta fraction of the expectation, this is like e to the minus delta square. Yeah, so this is like no, I would say it's 2 to the e to minus delta square qn over 3. That's the Chernoff bound I copied from somewhere. Okay, good. So the point is that I cannot deviate by more than constant fraction from this one, and this is a very, very fast decreasing function. There's an exponent, here's the expectation, here's the square of this fraction up there that somehow slows me down, but this should be like very, very tiny. Yeah, and I will use it for delta equal half, which means that there will be e to the minus expectation here, like e to the minus expectation over 12. So that should be very tiny. Okay, good. So I think I need to wipe out my process and go back to proving it. Yeah. So I'm wiping out the process because I think I want to keep the statement of the theorem still up there. So I'm wiping out the process. So now, so this is Chernoff we are going to use. So what I want to say is that A in expectation is twice log n times n, and I want to say that it will be like between 1 and 3 times. Yeah, so I want to say that the probability that the size of A over this log n times n to 1 minus epsilon is within the fraction 1 minus 1, 3. Okay, so the probability that, the expectation is 2. I can afford the constant deviation, but I don't know much, yeah? So this is really the Chernoff for delta equal 2, yeah? This is, so this is larger, yeah? Because this Chernoff for delta equal half, delta equal this is larger than 1 minus twice e to the minus expectation, so 2 log n times n to the 1 minus epsilon over 12. Okay, this is like I put the expectation up there. I'm happy. Good. Okay, so this is tiny. Yeah, this if n is large enough, and I can choose knowing epsilon, I can choose large enough. This is like larger than 0.99 for large enough. For large enough n. Okay. I mean, this is like super fast, super quickly decreasing function for A. Good. So A is very close to the expectation. I mean, I here used like off by a factor of 50%, but I could use even more. Good. But now I want to say that what a guy outside A, how many neighbors will we have? So try and think. Now we want to analyze the following thing, because we want to contract a guy onto neighbors. And the question is like, how many neighbors do we have to choose? Yeah? How many neighbors do we have to choose? And like, pick a vertex in G, and I want to, what's the expected size of how many neighbors this guy has in A? Well, there's some neighbors, okay? There's some neighbors, and this guy, there's some neighbors, and these neighbors actually, there's some neighbors, and these neighbors, like every neighbor gets independently selective probability P. Yeah? So this is P times the size of this neighborhood. Okay? So if this neighborhood, so remember that previously we had the average degrowth was n to epsilon. Okay, the average degrowth is n to epsilon. So what I want to say here is that if the minimum degrowth was n to epsilon, then we will be fine. Okay, then this will be still quite large because, yeah. So what I want to say is that if the degree of V is larger than n to epsilon, then this is larger than 2 log n. Okay? Okay, so this is larger than 2 log n, which means, again, the Chernoff, that the probability that this number of guys n of V intersection A is smaller than log n is smaller than, this is half of the deviation from the expectation. So this is again 2e to the minus expectation. So this is log n, 2 log n over 12. So this is really 2n to the minus 1 over 6. So this is again tiny and large. This is again smaller than 0.99 if n is large. No, but I want to do it, I want to do more. So this is like really tiny. This is much, I want to use the fact that this decreases with n. Okay, so this is like super tiny. Okay? It's like super tiny, which means that most of the guys will have got large, I mean the guys with high degree, most of them. Okay? So now, I want now to admit that I skipped one step that I want to get at the end and I forgot it. I want to first make an operation assuming that, so we had previously assumption that the density is small, it's large, okay? That there's more than 1 plus epsilon edges. So now I want to first make a simpler operation here. I want to here, sorry for this one, I want to here assume that minimum degree of G is at least n to epsilon. That every guy is, let's first do this case and then try to assume it later. So assume that not only there are a lot of edges, but also every guy inside, every guy has got, every guy in the graph has got, every guy inside the graph has got a lot of degree. Then this always happens, which means that every guy, that like a lot of guys will have got, means that a lot of guys, I mean, on average, a guy will have got 2 log n neighbors in A, which means that, yeah. So what I want to say here now, I mean, so this is like the probability. So in expectation, there will be like only n to the 5 over 6 guys with less than log n guys. Yeah? So the expected number of vertices V whose neighbors in A is smaller than log n is like 2 is smaller than 2n to the 5, 6, which means that there will be like very few of them. I mean, now we can use some Chernoff or even I think Markov. This is the expectation, which means that there will be like very few of them. Okay. So what I want to say is that now if I want to define now what I want to say, what comes from here, and I want to skip yet another Chernoff here, I want to say that if I define the set of B, these are the guys which are not in A, but they have got a lot of neighbors in A. This set is large. The probability that set of B is more than half of the vertices. This is more than 0.99 for large enough n. Yeah, and how does it come? Well, the probability that you're in A is like log n over n to epsilon. So this is small for large n. The probability that you have got this 1 over n 1 over epsilon. The probability that you have got there. I mean, now I skip this channel, but the fraction of the guys that has got less than log n neighbors is small, sublinear. The fraction of the guys that is in A is sublinear, because this was this one n to 1 minus epsilon, which means that almost everybody is not in A and has got more than log n neighbors in A. Okay? And now, this is very brute force statement saying that, okay, almost everybody means that at least half with good probability. Okay? I skipped here some Chernoffing on the last step, but I hope you'll forgive me. Okay? So I have got a lot of guys that have got large neighbor. Okay? And now I want to say the following. Let's make the following procedure. For each WB, do if there are UV in the neighborhood of B in A without non-edge, so that UV is not an edge, then contract W onto U. Okay? So what do I want to say here? The picture is as follows. I have got my set A here, and I'm investigating these guys from B one after another. Okay? And this guy has got number of neighbors, and I'm saying, hey, does this guy see a non-edge here? If there's a non-edge here in his neighborhood. Okay? If this is a non-edge, I'm contracting this edge. Okay? And now what happens, because these are both neighbors, and I'm contracting this edge, this will become an edge. Okay? Because, I mean, this was not an edge, and now this will become an edge. Okay? Good? Yeah? So whenever I do this, I add one more edge inside set A. Okay? Good? Else exception. Well, one exception, because this guy has got log n neighborhood, and what I'm really doing, I'm taking guys outside A and contracting onto guys in A. I'm making a one shallow minor. Okay? I never cascade contractions. I mean, this is like contracting onto guys in A. Okay? So this is really like one guy in A may have a lot of guys from B contracted onto it, but this is still a star. This is one shallow minor. Okay? I'm keeping a one shallow minor of G, and at some moment, if a guy here sees a clique, he sees a clique of size log n. That's his neighborhood. Yeah? This log n that was here before actually didn't have any constant, this omega up there. So this exception, which means that I see a clique of size log n. I mean, this is a log n in one channel minor. I'm happy. I mean, this is my exception I wanted. Okay? So I can, for the entire set B, I can make these contractions. Okay, into set A. And now what happened? Well, let's do the analysis. What happened? What happened? Well, yeah. Let's try to say here what happened. Well, I contracted onto set A. I ignore everything else. So now I make G output, so G tilde, to be like G of A after contractions, after this procedure. Okay, so after this procedure, I look at set A, and this is my output graph. So the size is like this one. So it's n to the 1 minus epsilon times log n. I promised roughly this size. Okay, so number of vertices is roughly n to 1 minus epsilon times log n. But how many edges do I have? I have at least n½ edges. Yeah, because that's the size of B, and every guy from B gave me a new edge. Yeah, the number of edges is at least size of B, which is at least n². Okay? Good? So I have what n to the 1 minus epsilon vertices, log n is like lower order term, I mean, it doesn't count really here, and I have n½ edges. Yeah? And what I promised, now there's I think I want to wipe out the lower denseness thing, so let's do the following. So the output had the following. It has got roughly n to 1 minus epsilon log n vertices, okay, and has got at least n half edges. Okay, and now maths say that n half is roughly n to 1 minus epsilon log n. Well, what's the power we need to insert here? It's not 1 plus epsilon, it's 1 plus epsilon squared. Yep, that's like even like I mean even more. Yeah, I mean there's something more. Like if I put just this one, this, and this will be like n to the 1 minus epsilon squared. I need to add more. I need to add roughly epsilon squared here. Actually, even something more. Yeah, I need to add epsilon cubed, epsilon whole. Okay, barring this log n. I mean this log n is some lower order term we need to take care of, but I'm just saying that this is actually larger than this for large enough n. Yeah, because the exponent here will be like 1 minus epsilon. So this one is below 1 minus epsilon cube, because this is like 1 minus n to 1 minus epsilon cube times log n something. But for large enough n, this will be like worse than this log n won't save. Okay, so yeah, so this is really like output out of edges. Okay, so what we gained here, okay, I think I need to wipe out the statement, but that's, I hope understandable. What we gained here, we started with a graph G that had got n vertices and minimum degree n to epsilon, this n to epsilon, and got G hat, which had got roughly n to 1 minus epsilon log n vertices and at least n over half edges, and we observe that if we define this one to be n hat, then this one is larger than n hat to 1 plus epsilon square, which was what we wanted. Okay, this is like higher density. The only thing that's missing is that to get from average to minimum degree. Okay, we started here with a guy of minimum degree, and now we wanted to get to more degree, but that's actually something we actually did on tutorials the previous week or the previous week. So that's actually easy. I'm going back here. So this is something we actually, in some sense, it appeared inside some guys on tutorials already. So the final lemma, final observation follows if I have got a graph G which has got n edges, n vertices, and at least d times n edges, then there exists a set. A inside V of G, which is large. Size of A is at least root n. That has got good minimum degree, such that minimum degree of G of A is at least D times size of A. It's at least D. Yeah, the minimum degree is at least D. Okay? Yep. And I think I need to, I think maybe there's some off by 1 error here, but this is a proof. Well, what's the proof? I mean, what can we do with a vertex that has got smaller degree than D? Okay, we just need to remove it. Yeah. Okay, like while A side is the entirety of G, while there exists V in A which has degree or V in G of A is smaller than V minus 1, removing A minus V. Okay? Okay? And now the point is that before we, now we want to argue that, well, if I make A iterations, I remove A vertices, so size of A is n minus A, but I remove only the number of edges. is at least like the starting point, and at least every step I remove the minus 1 edges. Okay, I remove the minus 1 at every edge. So the every point, in some sense, I mean, I'm having this one extra edge more. On average, there are d edges per vertex, and whenever I remove a vertex, I remove one vertex, but only the minus 1 edges. Okay, so this extra edge accumulates per vertex, and at the moment of root n, you start to have got too many. So this, what I'm just saying, that this is always larger than n. There are always n edges. As I progress, there are always n edges. I mean, because I cannot, I mean, if I remove n vertices, I remove n times the minus 1 edges, and there are the n edges to start with. Okay? So there's n edges, which means that I need to stop before root n, because at root n I don't have space for n edges. Up there. Okay? This is like, there's a tiny gap between between the average degree, the average number of edges per vertex, and how many I remove at every step, and this error accumulates, and it, I mean, so at the end I still have these n edges, which means that I cannot get down to more than root n vertices. Okay? And this is what we really want, yeah? What we are really doing here now is that we do round robin. Yeah, we start with our vertex gi. We make this operation to get like, so this is with n vertices and like n1 plus epsilon edges. Okay, this gets like gi, I would say gi bar. No, bar is wrong thing. Tilde, which has got at least root and vertices, like n tilde at least root and vertices and minimum degree at least n to the tilde to epsilon. Yeah, so we swapped average degree for minimum degree. Then we do the operation that gets some gi hat. So this g hat that has got, again, now this one gets to 1 epsilon, so this n hat is at least this, the n tilde 1 minus epsilon, which is at least root n to half minus epsilon half vertices, and edges at least n hat to 1 plus epsilon square, and then we loop this field. Okay, that's our operation, and here possibly we get this kt for c in omega. Okay, as a one shallow minor. Okay, so here we take a subgraph, and here we take one shallow minor. Okay, that's the structure of what we are doing here. Yep, so just to repeat, what we are doing here and up there is that we have our graph, which has got a lot of edges. We first sacrifice, like, shrink to root n size of the graph, swapping the average degree for minimum degree using a simple, like, counting argument. This is not something sophisticated. Here comes the main trick, that if we choose 1 over n to the epsilon roughly fraction vertices at random, then you can contract the rest onto this chosen subset to increase the density, because if you cannot, you have got a huge clique there, and that shouldn't happen as a one shallow minor. So that you have got one shallow minor that increases the density, but you cannot go around the cycle more than to the 1 over epsilon squared times, more than 1 over epsilon squared times, because that would increase your density above n squared. I mean, the number of edges above n squared, which means that at some point, the exception being the large clique happens, and this is a constant shallow minor of log n size, which means that you cannot be too large to start from. Okay. The problem is that now this final m of epsilon, this lower bound on the size of the thing, is quite huge, because we need it in a few places. So at the end, at the punchline, when we say that, let's do a small analysis. I mean, there's a formal analysis in the notes, but let's do a hand-wavy analysis. The final punchline is that, hey, if you come up with this KT is of size log n, but actually it cannot be larger than the corresponding shallow minor, which is like 2 to the 1 over epsilon square shallow minor. So here, the size of the graph needs to be exponential in the forbidden clique shallow minor at depth 2 to the -1 minus epsilon. So this is square, so this is already large. Yeah. So this final, yes, the final thing. Let me write it here. So what we have here is that, yeah, so we need to start, yeah, so at the end, and the size of v of the n I needs to be at least like 2 to the, there was like 2 to the 1 over epsilon square f 2 to the 1 over epsilon square. So this is like the density, the shallowness of the shallowness of the minor, and you cannot have clique of this size, and there was this constant up there. Yeah, and at every step you square root it. Yeah, so there's like this one, so at every step you square root it. So it's again so, and the starting point is to be 2 to the 1 over epsilon square times f 2 to the 1 over epsilon square. Then every step you square root it. So this adds this one here. And there's also a few things of lower order, I would say, that's saying that, hey, actually at many steps, I was doing this Chernoff stuff, but in a lot of the Chernoffs I said, hey, this Chernoff actually, this is actually 0.99 because n is sufficiently large. Yeah? So at every step this n is sufficiently large, but this is like completely lower thing compared to this. So this is like the huge part, and this Chernoff things. We also need to take care that this p that was here just before is lower than 1 for all these inequalities to work. So this log n over n to the epsilon needs to be lower than 1. But this is still some small thing compared to this. So this is like the bad thing we get here. But maybe, but there are some proofs getting better. But this is actually the proof that I could present for you in this like an hour or something like that, or actually less than an hour. So the punchline of the lecture, I'm concluding now. The punchline of the lecture is that, hey, actually nowhere dense graphs are sparse. I mean, from the fact that you don't have a large shallow clique, actually we deduce that the average degree is n to epsilon, which is, if you think about it, this is somewhat a surprising dichotomy. I mean, if you have got a graph class, you either obtain all cliques as shallow minors, so this is somewhere dense, or if you don't obtain all cliques as shallow minors, I mean, if for every dense shallowness, the depth, for every depth there is some clique you don't have there, then actually all the graphs need to be really sparse. I mean, there's like n to the epsilon average degree times some constant depending on epsilon. Okay, so there's a dichotomy. There are no graph classes in the middle. Like, I mean, you either have got a lot of edges because this shallow minor, arbitrary closed clique means that as a shallow minor you get arbitrary dense graphs, quadratic size, or you always have got n to epsilon density more or less in shallow minors in the graphs. So that's like somewhat surprising. And I think I want to conclude now. I don't want to extend. Thanks. Next, there's tutorial when we'll be practicing some this shallowness and this density arguments. And next week we start with generalized coloring numbers, which is, I think, my favorite part of this theory, where we'll be raising the degeneracy. You remember this weak coloring and strong coloring. Strong coloring are in the notes, but there was this weak coloring and strong coloring I did on the first lecture. And now we'll be doing the same, but we're replacing the infinity up there by bounded radius of the paths, and saying that this has got a lot to do with what we did so far here in the last two lectures. Thanks.